8. Internal forced convection. Welcome to internal forced convection. Internal forced convection happens when the fluid is forced to move inside a boundary, like inside a pipe or a duct. This is different from external convection, where the fluid flows over surfaces like cars or planes. Why does it matter? Because the rules change. Inside pipes, the walls fully enclose the fluid, so the boundary layers grow until they meet in the middle. This affects both the velocity profile and heat transfer rate. You'll see internal forced convection in everyday systems, air conditioning, oil pipelines, engine cooling, and even your home's plumbing. By understanding it, you'll learn how to design systems that move fluids more efficiently while controlling temperatures effectively. In this chapter, we'll break it down step by step so you can confidently apply the concepts to real-world problems. Learning Outcome 1. Here's what you'll walk away with from this chapter. You'll start by understanding how velocity and temperature behave inside ducts and pipes. Unlike external flow, here the fluid is fully enclosed, so the flow and temperature profiles evolve differently. Then we'll look at entry lengths, how far fluid travels before reaching a stable profile. You'll analyze both hydrodynamic and thermal development because both matter for accurate design. Next, we'll define 3 flow regimes: laminar, transitional, and turbulent, and you'll learn how to recognize and calculate for each one. You'll also be able to calculate pressure drop and heat transfer in fully developed flows, which is vital for systems like HVAC and power plants. We'll introduce friction factor and Nusselt number as tools to help quantify performance. And finally, you'll learn how to apply empirical correlations to real-world calculations, like estimating how much pumping power a system will need. If you can do all that, you're ready to design smarter, more efficient thermal systems. 2. Introduction to internal flow. Let's get clear on what internal flow actually means. Internal flow happens when the fluid is completely trapped inside something, like a pipe, a duct, or a cooling channel. There's no open boundary like in external flow, which completely changes how the fluid behaves. In these cases, flow is pushed by mechanical force, a pump or a fan forcing the fluid to move through heating or cooling equipment. You'll also see 2 important regions. The hydrodynamic entry region is where the fluid velocity profile is still forming as the boundary layer grows from the walls. Meanwhile, the thermal entry region is where the temperature profile starts to settle as the fluid heats up or cools down. Internal flow is what powers modern energy systems, from power plants to refrigeration units, so understanding these regions helps you build more efficient designs. 3. Flow classification in internal convection. Let's talk about how we classify flow inside pipes and ducts. The first step is always the Reynolds number. This single value helps you figure out whether the flow is calm, unstable, or chaotic. If the Reynolds number is below 2300, you have laminar flow, smooth and predictable. Between 2300 and 10,000, the flow is in transition. It's unstable and can fluctuate. Above 10,000, it's turbulent, high energy, chaotic, and fully mixed. For non-circular ducts like rectangular channels or complex shapes, we don't use diameter directly. Instead, we use hydraulic diameter. It's based on the cross-sectional area and perimeter, helping you apply the same flow calculations to any shape. The big takeaway: Reynolds number tells you the flow regime, and hydraulic diameter lets you apply the same rules to pipes, ducts, or any channel, regardless of shape. 4. Hydrodynamic and thermal entry lengths. Let's simplify how entry lengths work in internal flow. When fluid enters a pipe, it doesn't instantly develop smooth profiles. It takes some distance before the velocity and temperature settle into a stable pattern. This is what we call the entry length. For velocity, it's the hydrodynamic entry length. In laminar flow, it's about 0.05 times the Reynolds number and diameter. In turbulent flow, it's simpler, about 10 pipe diameters. For temperature, we have the thermal entry length. It follows a similar rule.
around 0.05 times Reynolds, Prandtl, and diameter in laminar, and about 10 diameters in turbulent. Once the flow travels beyond these lengths, it's called fully developed flow. At that point, velocity and temperature profiles stop changing along the pipe, making it easier to analyze and predict performance. Bottom line, know your entry lengths to avoid miscalculations early in the flow, especially in short pipes or channels.
5. Velocity and temperature profiles. Let's look at how velocity and temperature behave inside pipes. In fully developed laminar flow, velocity follows a parabolic shape. It's fastest in the middle and zero at the walls. The maximum velocity is exactly twice the average velocity. This means flow near the center moves much faster than the bulk average. Temperature is a bit different. It depends on how we heat or cool the pipe. If the surface has a constant temperature, the Nusselt number is always 3.66, very predictable. But if the pipe is heated with constant heat flux, the Nusselt number increases slightly to 4.36. This simple breakdown helps you quickly estimate heat transfer in laminar pipe flows without complex calculations, especially useful in early design stages. 6. Heat transfer analysis. Let's make heat transfer analysis simple and useful. The total heat transfer rate in internal flow is straightforward. It's just mass flow rate times specific heat times the temperature change between inlet and outlet. This tells you how much energy the fluid is carrying. If you have constant heat flux, you calculate the outlet temperature based on how much heat is added along the surface. The relationship is linear. More surface heat, higher outlet temperature. If you have constant surface temperature, the formula shifts. Now it's about how the surface drives heat into the fluid using the heat transfer coefficient and the log mean temperature difference. In both cases, these formulas help you quickly predict how hot or cold your fluid will get, without complicated simulations, just from basic flow and surface data. 7. Friction factor and pressure drop. Let's make pressure drop easy to understand. Whenever fluid flows through a pipe, it loses pressure because of friction along the walls. This loss is called pressure drop, and it's directly linked to the friction factor, pipe length, diameter, and fluid velocity. For laminar flow, there's a simple rule. The friction factor is 64 divided by the Reynolds number. The lower the speed, the less friction you get. In turbulent flow, things get more chaotic. We use the Blasius correlation, which shows that the friction factor drops as flow becomes more turbulent, following Reynolds number to the minus 0.25 power. Knowing these relationships helps you avoid underestimating pumping costs and ensures your systems are designed for both energy efficiency and reliability. Let's wrap up with how to estimate heat transfer using Nusselt number correlations. In fully developed laminar flow, it's easy. Nusselt number stays constant. It's 3.66 for constant temperature and 4.36 for constant heat flux, no matter the Reynolds number. For turbulent flow, we use empirical equations. The classic one is the Dittus-Boelter equation, which depends on Reynolds and Prandtl numbers. You'll use 0.4 as the exponent when heating and 0.3 when cooling. If you need more accuracy in turbulent flow, especially in engineering designs, the Ginialinski correlation is your friend. It uses the friction factor directly and adjusts for flow properties, giving you a more precise prediction of heat transfer rates. These correlations save time. No need for simulations, just plug in the numbers and get fast, reliable results. 9. Effect of surface roughness. Let's talk about surface roughness and why it matters. In turbulent flow, the roughness of a surface doesn't just sit there. It actively affects how the fluid moves. Specifically, it increases both the friction factor and heat transfer rate. This means a rougher pipe wall will cause more resistance to flow, but might also boost heat transfer. To account for roughness in your calculations, engineers use two practical tools.
The first is the Moody chart, a quick visual guide that shows how friction factor changes with Reynolds number and roughness ratio. The second is the Colebrook equation, a mathematical tool that connects friction factor, Reynolds number, and roughness ratio. So, whenever you're working with turbulent flow and rough pipes, don't ignore the surface texture. It has a direct impact on how much energy you'll need to pump fluid and how effectively you can transfer heat.
10. Flow in non-circular ducts. Let's make non-circular duct flow simple and practical. Not every pipe is round. In many real-world systems like HVAC ducts or heat exchangers, you'll deal with rectangular or annular ducts. Luckily, you don't need entirely new formulas. You just use the hydraulic diameter, which adapts circular flow equations to any shape. For rectangular ducts, you calculate it from the cross-sectional area and perimeter. For annular flow, like in double-pipe heat exchangers, it's even easier. You simply subtract the inner diameter from the outer diameter. This hydraulic diameter shortcut keeps your calculations consistent and saves time when designing complex duct systems. 11. Transitional flow in pipes. Let's break down transitional flow in pipes, an area where things get unpredictable. When flow moves from laminar to turbulent, it enters a transition zone. This zone isn't easily described by theory, so we rely on empirical correlations to bridge the gap. These correlations give us practical answers when theory falls short. Interestingly, heat transfer actually increases during this transition because flow instabilities boost mixing. That's why transitional zones can improve heat transfer without fully entering turbulence. But transition is sensitive. The way fluid enters, whether through a sharp edge or a rounded inlet, can either delay or accelerate turbulence. That's why entry geometry is crucial in pipe design. Bottom line, understanding transitional flow helps you avoid surprises in both energy efficiency and system stability. 12. Microscale convection and mini and micro tubes. Let's finish by talking about how things change at the microscale. In mini and micro tubes, the heat transfer behavior shifts because surface effects dominate. You can't just apply normal pipe flow equations. Heat transfer mechanisms evolve at small scales. One key change is that transition from laminar to turbulent flow happens at much lower Reynolds numbers in microchannels. So you'll see turbulence effects even when flow rates are low. Also, because small channels have a high surface-to-volume ratio, heat transfer becomes much more efficient. This is why microtubes are popular in cooling electronics and compact heat exchangers. At small scales, surface effects rule. This is where design innovations can make the biggest impact. 13. Engineering applications. Let's wrap up by seeing where all this theory turns into real-world applications. Internal forced convection plays a critical role in many engineering systems. For HVAC systems, understanding flow in ducts helps design efficient air distribution and cooling coils. In heat exchangers, especially tube banks and compact designs, accurate heat transfer predictions lead to better thermal performance. Electronics cooling is another big area. Liquid cooling in CPUs relies on forced convection to keep devices from overheating. And in oil and gas pipelines, optimizing flow conditions reduces pumping costs and improves overall energy efficiency. Across industries, understanding convection helps engineers improve system performance and save energy.
Summary. Let's close by pulling everything together into a clear summary. Whenever you're analyzing internal forced convection, your first step is always to check the Reynolds number. It's the key to deciding if the flow is laminar, turbulent, or transitional. Then think about entry lengths, both hydrodynamic and thermal, since they tell you how far it takes for flow and temperature profiles to fully develop. Pumping power is directly affected by friction factor and pressure drop, so minimizing losses is crucial in design. Heat transfer is not just about the fluid, it's also about the regime it's in and how the surface interacts with the flow. Empirical correlations are your practical tools. They save you from complicated calculations while still giving reliable estimates.
And finally, don't forget microchannels. When size scales down, behavior changes. What works at large scale doesn't always apply in micro devices. The summary is simple. Know your regime, use the right tools, and always match your design approach to your system's scale.